acts as
A base.
a base. Sodium hydride can only act as a base. The sodium cannot stabilize the hydride at all, okay? Which means that hydride is going to react as swiftly and quickly as possible. That means base. So it's going to remove an acidic hydrogen. There are two of them in our structure. We've got our purple ones or our red ones. Which ones are more acidic? The purple, because
It had to mix with the nitrogen and the oxygen.
we have two resonance options. We can either go in towards the nitrogen or, and because everybody seems to be having problems drawing resonance, probably because I've been lazy about it, or we could take those electrons and we can move them into the structure. Okay. So we have three resonance structures, and this is going to be the next thing. There's been getting people saying, well, how do I go from this resonance structure on? It's not where the carbon is negative. Does the carbon have to show a negative charge to be an active nucleophile? No. So in that bottom structure, how can I show it react? Sorry, I just lost track of what I was drawing. With the Michael acceptor. Well, I want the negative carbon to react, but the oxygen's negative. Okay, or technically here. That's now the negative carbon attacking. Okay, I don't have to start from the structure with the carbon holding the negative charge. I could start from any one of these. Okay? If we went, we'll go green. That does the same thing. Okay? So this is the beauty of resonance. You can have any atom or any negative atom attack from any one of your resonance structures because they are all identical. It just means showing more arrows. That's okay. Okay, so we now have two possible attacks, red and purple. The red attack is attacking at, or is going to produce which product? Our 1,4 addition, also known as our conjugate addition, also known as
Kinetic? Do you want to know? Gosh darn it!
That's why I kept delaying. I was hoping you were going to give me a different answer. The purple one would be the 1,2 addition, also known as the, and I'll call you out, Corey. Let's share the pain.
What was the question? 1,2 addition, also known as the
The, so I can accept kinetic, but I want another answer. And I know you and I talked about it.
kinetic conjugated.
Nope, conjugate was our thermodynamic.
Oh, direct
Direct.
addition.
Right? So we have all of those possible options. How do we decide which option is correct?
Strength and reversibility of the nucleophile.
Okay? It has to do with strength and reversibility. This is why we had all those energy diagrams. Our kinetic product will always form first, every single time. Okay? But if that reaction is reversible, well, then the thermodynamic product wins out, because the thermodynamic product is always irreversible because of how low in energy it is. That's why it's the thermodynamic product. Okay. How do we tell if our reaction is reversible or irreversible? That means we have to look at our nucleophile. Okay. We would compare our nucleophile to the products produced. Oh, that arrow is going to get in the way, so I'm just going to erase that. So if we went through and did the 1,4, what happens? Oh God, this is going to be ugly. Sorry, it's going to take a little bit of time here. 1, 2, 3. Well, that wasn't too bad. Versus our direct. We're attacking negative oxygen. Yes? In deciding between these on which product should actually form, what we have to evaluate is our strength of our nucleophile. Our nucleophile was found in these 3 species. Okay. What is the most stable form for our nucleophile? I left off the minus sign. Which one? Top, middle, bottom? Why the bottom? Oxygen can carry that negative charge better than all the others. So when I compare across my reaction, okay, and that reaction that we're comparing is what we've got as our red arrow and our purple arrow, which I now kind of covered over in black. I want to compare those to the reactive species in those products. So in the red reaction, I'm looking at a negative oxygen. In the purple reaction, I'm looking at a negative oxygen. What is the difference in stability between a negative oxygen and a negative oxygen? Nothing. What does that mean? That reaction is reversible. Okay. If it is reversible, which product do I get? I'm going to get the thermodynamic product, the most stable product. Well, why is the thermodynamic product more stable?
Because it's irreversible. Oh, why is it more stable?
It's not really conjugated.
Because
It's got resonance.
Are you just guessing?
Oh, I can see it.
Okay, just checking. I'm just curious. So if we highlight in green, which I know doesn't stand out,
Is there a steric hindrance on the kinetic side? Or like, 'cause
a,
you have
a little bit,
oxygen
but
and
a little
nitrogen
bit, but we
close
don't
together?
want to consider that. It's more our electronic effect. Sorry for moving the table on you. See the green pi bond in both cases? That's our big characteristic difference between those two, is the difference in stability between those. Why is the red one more stable than the purple one? Well, as Sean suggested, what do we have? Resonance. If I have resonance, what does that do to its stability? Makes it more stable, which drops its energy, hence I get the thermodynamic, or that would then be the thermodynamic product. The kinetic one, if we look at that pi bond, what stabilizes it? Really nothing. Okay? So that is going to be higher in energy because it is not as stable as the red one. Okay? So what we're evaluating is we're looking at all the possible reactions that can come out of this, and then we have to decide which one wins. Okay? That win argument goes back to comparing the strength of the nucleophile across the most reactive species. According to our nucleophile comparison, it is a reversible reaction. If it is reversible, I get the thermodynamic product. Okay, so I end up getting the red one, which is really, really fun. We'll call this the reversible nuke. The kinetic we'll call the irreversible nuke. Why does this become really fun? The thermodynamic product, is it reversible? No. So while using a reversible nuke gets me the thermodynamic product is irreversible as a product. That's not confusing at all. Okay. And all of that hinges back on the strength of the nucleophile. Okay. Because that last part can change for the kinetic product, it being reversible or not. Okay. So in this case, what do we end up with? We end up forming the thermodynamic product. So we can erase our kinetic. We should officially show the resonance structure. Why should we show the resonance? It explains why this is the product. If I don't show that resonance, I don't have a clean explanation of why that is my product. So I want to add that extra layer of information. Okay. What can happen now? I can find a hydrogen from somewhere in solution, which I'll just call HB. We can protonate, and we would end up with our final structure, not confusingly at all. Whoa. Sorry, that was just weird. Stacked on top of everything. Questions about any of that? Okay. This is interesting chemistry. It also ties in a lot of stuff. We've got thermodynamics, we've got kinetics, we've got reversibility of our nukes. Okay? We've got reversibility of our reactions. We have conjugate addition, direct addition, 1,4, 1,2. Everything we've talked about folds into this one simple problem. Simple. Shouldn't have said simple. One massively simple looking question. Okay? And you're responsible for being able to answer each and every single one of those questions all the way down. It requires a logical organization of thought through the whole process. I'm not saying that's easy. Okay? In fact, I think that is extremely difficult, but that is what you are responsible for doing. How do you do that? Practice. Okay? Is that a question, Corey?
Yeah, can you explain the reversible nuclear part and the irreversible?
So what we are deciding is when we first had our branch choice between our thermodynamic versus our kinetic product. We're just trying to decide which one should we get. Okay, that decision comes down to the reversibility of the nucleophile. If the nucleophile adds reversibly, I will get the thermodynamic product. It's because as soon as I form the kinetic, what happens? It turns around, goes back to the reactant, I can make the thermodynamic product. Okay? How do I know it's reversible? Okay. Well, the reversibility has to do with the most reactive things in that step. Okay. My product has a negative oxygen versus a negative oxygen as my nucleophile. Well, which one is more stable? Negative oxygen or negative oxygen? They're the same, which means that reaction is reversible. Okay. Believe it or not, you've done this same thing before in general chemistry when you looked at the strength of your acids and bases. You looked at pKa's, okay, calculating the concentrations of conjugate acids and conjugate bases and all that fun stuff. You're doing the same thing. You just attached numbers to it so you could just punch it into a calculator and say you didn't have to think about it. Unfortunately, we have to think about it here. Okay. But the good thing, you don't have to punch it into the calculator. You just have to think about it. Okay? Questions? And it disappears. The enamine, if we go all the way back to it, the enamine has some special chemistry associated with it. If we took our carbonyl and just added our nitrogen, in fact, a secondary amine, we would end up at the enamine. We don't form the imine. Okay? Remember, if that was a primary nitrogen, what would have happened? So primary nitrogen means just one R group. When it goes through to react, we would form the imine. Why, when we add a second R group, do we all of a sudden not see the double bond between the nitrogen and the carbon? The nitrogen is positive. There's no easy hydrogen to remove to neutralize that nitrogen. So instead, what happens? We remove a hydrogen from one of the alpha carbons to form the enamine. Okay? Nifty little structure. Okay? How would we predict it to act? 1,4 addition or 1,2?
1, 2.
Why 1,4?
Because it's got resonance, so it's more stable, so it won't.
It's the same thing as an enolate. There is no difference between the imine, enamine, and an enolate. They're the same kind of tautomerization relationship between them. So if the enolate attacks as a 1,4, we would likely expect the enamine to do a 1,4. Okay? They have an extra benefit. They favor the kinetic enol form. Okay, what do we mean by that? If we went through and looked at, say, a carbonyl compound, we have two possible enolates that could come out of that, right? Where we have the more substituted double bond versus the less substituted. The more substituted would be the thermodynamic, and the less substituted would be the kinetic. And when we're looking at an enolate, we really have both those options available. But what happens if we switch this over to the enamine? Oh God, that close enough. Jiminy Christmas. It's not getting better. There's carbons up there. We'd still expect a thermodynamic and a kinetic enolate. But this is saying that we benefit the kinetic form over the thermodynamic. Which is kind of odd, because if we went back to our enols, we would typically see the thermodynamic. And why would we expect to see the kinetic? Now, we haven't gone back to this explanation for a while. Believe it or not, it's sterics.
Oh, because the inability to remove that hydrogen, the tertiary position, or
All of those atoms are locked into the same plane. Okay. In fact, we also have that. What do we have bumping up there? Hydrogens. The thermodynamic product has all of those atoms bumping against each other. Is that a good thing? No. So we don't like that. What happens in the kinetic? It's not that it can rotate. It can't rotate.
also it can't rotate to do.
Okay. Our steric hindrance was coming from the hydrogen off of the methyl group. Do we have a methyl group in the kinetic position? No. There's less steric hindrance there, which is why we end up favoring the kinetic product over the thermodynamic. This allows for much more selective substitution, because now I can say that that is my nucleophile. Okay, why is that important? Well, I can now attach things at that position as opposed to the other one. Okay, selectively. That selectivity comes into play in, I don't know, making, say, the Whelan-Mischer ketone from the lab, for those of you that might be wondering. Okay. So we addressed this. We've got our 1,4. One of the other things that's nice about our imine, or our iminium, or our enamine, what would they react with? Rhymes with electrophile. Nucleophiles, like, say, water. What happens when water reacts? We can eject the nitrogen and we end up right back with our starting carbonyl. Okay? It is very easy, reversible chemistry, super, super convenient. Okay? So we can change and now selectively do substitution where we want to on a base carbonyl structure. Okay? By converting it first to the enamine, do the chemistry you want, remove the enamine, you're right back with your carbonyls. Kind of sweet. Okay. Also relevant for lab. Okay. No. The Robinson annulation, we could look at that. Reagent necessary to follow this synthesis. You guys want to try and give this one a shot? Sure. Okay. Formats. Try to do some color coding in here. So in that first step, we've got two parts, or two steps. And we notice that in the product I've highlighted the red, because that's the red that matches there. So the piece that's missing would be this guy. So as Corey was pointing out, this looks suspiciously like an aldol condensation, okay, which, hey, maybe it is. Okay. So if that was the case, then I would need to replace that piece, right? And because that looks like a double bond or a weird scribble, let's fix that. Okay. Let's ignore the fact that I put it next to the 2. Okay. If I just mix those 2 species with each other, the red and the black, would I get that product? Why not? What's that? I don't have a nucleophile. Okay. I need the aldol reagent, which is our nucleophile. I need to get a nucleophile. Which of those species needs to be a nucleophile? Red or black?
Red.
The red. How can I make sure that it converts entirely into a nucleophile? I need to add an irreversible strong base like
NaH.
sodium hydride or LDA, lithium diisopropylamine or amide. That gets me that intermediate. But then I have to continue on down to that big nasty looking thing. So again, I would try and find the similar pieces. Okay. The parts unhighlighted are what we started with. The parts highlighted are purple and blue. Suspiciously, I colored the 1 and the 2 purple and blue. Wonder why that might be. So, what was your cell?
What was before the second arrow?
Okay,
You
that's fine.
don't need to do a 1-4 addition.
There's no 1-4 addition to do. We are making a product that could do a 1-4 addition. You might talk to me after class to see what I see. Maybe you came up with a different way to do it.
No,
Okay.
I got stuck on 1-4.
When we move to purple and blue, believe it or not, purple needs to be what? This would be the time to speak up, Jen.
A 1-4 addition?
That needs to be our 1-4 addition, and the blue needs to be, and that's actually kind of weird. It doesn't quite fit a 1-4 or a 1-2. But the purple one for sure needs to be a 1-4. What am I placing? An ethyl, a CH3 and a CH2. What charge does that CH2 need to be?
Negative.
Negative. How can I make it negative? What's that? Could add a sodium. Okay. I could add a magnesium bromide, and I'm going to ignore those of you saying copper for a moment. What's the issue with making it a Grignard or an organolithium reagent? Those give us a direct addition. Crap. That would give us the 1-2, not the 1-4. So I need a carbon that is negative that gets me a 1-4. This is your specialized reagent. This is a Gilman reagent. This has to be your copper. Okay.
So it has 2 of the ethyl groups.
It has 2 ethyls, 1 copper, 1 lithium, and only 1 attaches. Okay. The result of that nucleophilic attack is what? We end up with a resonance structure, or we could show a resonance structure. What do we have if we actually push this resonance structure a little bit further on? We have a carbon nucleophile. So what can I do in the second step?
Substitution.
I can do a substitution and add my carbon electrophile, CH3, CH2. How many carbons is it? 2, 3, 4. And that needs to be an electrophile. How do I make it an electrophile?
Add a halogen.
Place a halogen. 2 steps, I've got my reaction. Make sense? Okay. So we're trying to find pieces, come up with ways to connect those pieces, and work our way through it, slowly and carefully. It takes practice to recognize where things are. Keep practicing. After that, we've got chapter 19, which is all about synthesis and then reduction and oxidation. So a lot of this is just going to be kind of a skip through. If we go through and look at trying to connect those, okay, they wouldn't connect. Why would the carbons not connect?
Because they're both electrified.
They're both positively charged. How could I make a carbon attack? And which carbon could I make nucleophilic? How can I make the one bonded to an oxygen nucleophilic? If I look at resonance, what happens? The oxygen takes electrons and it becomes positively charged, not nucleophilic.
We do a substitution of the Br to make to something that might be more.
Say like lab.
Oh, yeah.
What do I now have? I have a good nucleophile in the Grignard reagent that can attack. What I've done is very quickly change the charge on the carbon. Okay, I started positive and I became negative. To do this step, for some reason, some German came along, pretty sure they're German, and named it an Umpalong. Probably because they watched too much Willy Wonka. Okay. All we're referencing there is altering the charge on an atom. It may start positive, but at the end of that step it becomes negative. The Wittig reagent is an example of this. The Grignard reagent is an example of this. Okay. The Gilman reagent is an example of this. Okay. All we're doing is just changing that charge. So what we have to do is recognize ways that we can change that charge. That's why the Grignard, the Wittig, and the Gilman are all really important reagents, okay, because we can quickly change the charge on a carbon. Okay. That's our organic organometallics. I'm not sure I really have anything to add there. Reactions that form our carbon-carbon bonds. We've seen a bunch of these, but what they're trying to list in your textbook is just some reagents that can go through and give you carbon-carbon bonds. Okay? So it's a different format for your synthesis. What is your product? What was your reactant? When did they discuss it? Okay? Kind of neat. I personally find it confusing as all get out, so I'm just going to kind of mention it, say it's there. But I have talked to some people that really like it, so I'm pointing it out. Okay. A few more of them. Okay. Selective reactions. So when we're doing synthesis, we want to focus on selective reactions. If we take a look at that starting material, okay, what happens under those conditions? Okay. If I want to do just a substitution, I'll probably switch to the chloride. Why not use hydroxide? Wasn't that OTS, or tosylate, a good leaving group? Can I have hydroxide come in and do that? Chloride could do it. Why can't hydroxide? It's also a strong base. So it's not that it can't do the substitution. It's that it also does the elimination. So when we're picking our reagents, we have to be careful and realize that we're only running one type of chemistry, not two or three. When we go through and take a look at the selective reagent for the elimination, notice they did not write OH minus. Why not OH minus? Same thing, but reversed. It would also get me substitution. So I want to be careful in my choices to make sure that I don't end up with this multi-product issue. Okay. Why is that? What is the name of that base, out of curiosity? I'll accept sodium, but not necessary. It is T-butoxide. T-butoxide is our classic bulky base. It really only acts as a base because it's bulky. It can't get in to react in the center of a molecule to be a nucleophile. Okay. The next big section within this chapter looks at a whole bunch of reduction reagents. Okay. I'm not going to go into any real detail with these because the video kind of went into them. Does anybody have any questions from the video about any of these? No? Okay. In theory, just for the record, all of these are review, and all of these are new. This one plays a double role. Why does that one play a double role? It's our Wolff-Kitchener reduction, if we wanted to name it. Yep. It's our nitrogen nucleophile giving us an imine. Okay, so that goes back to our imine products out of chapter 18. Okay. Why do I need so many different choices?
Selectivity.
What's that?
Do you want certain, so you can have choices of selective?
Goes back to that selectivity argument. If I take a look at the Wolff-Kitchener, what does the nitrogen act as? A nucleophile. What if I have multiple electrophilic sites in my molecule? That nucleophile could react at multiple sites. What is KOH? A strong base. What if there was something acidic in my functional group or in my structure? Okay. The Wolff-Kitchener is not going to be a good reduction option. Okay. So I have to be considering the rest of the structure and saying, does the rest of the structure impact something?
I had a question on that then, because in that picture though, it does have the OIH on the carbonyl. Wouldn't that be acidic? If that was a carbon. Why would they show that hydrogen there?
It was a nice dodge, saying they. That was me. That hydrogen?
Well, they have an R, oh, is that like an R group or an H group?
That's what it is. It's an R or an H. Okay. Which, whoops, you're right. Even if it was a ketone, we do officially have a potential acidic hydrogen there. But it's going to come down to the rest of the reagents. Okay. What is the overwhelming majority of them going to do? Okay. So we can already start to see that we're going to lose some product along the way because there's all sorts of other things that could potentially happen. That is going to be one of our issues, which is one of the reasons why when we move into second semester, the yield of our reaction stops being close to 100% and starts to drop. Okay? But even with that extra kind of functionality of that acid characteristics, we're still looking in the order of, I think, 80% for our yields. Why do we not panic about yields in the lecture? It's a really simple answer. What is lecture? How many questions have you ever seen in lecture about yield? Not really any. Okay. Those last three reagents, or those last three reducing things, reagents, what else is particularly special about them when it comes to a carbonyl? Let's say I had taken that ketone and I'd used just H2 and platinum. What would I have gotten? What's that?
Would you still get the H, the carbonyl replacement? Oh, yeah, no.
Just add H across the pi bond, which means what am I still left with? The oxygen. What is special about the last three? There is no oxygen. We completely remove it from the structure, which makes things really crappy for you trying to do synthesis, because we could give you a final product that has virtually no reactivity in it. You'd be like, well, how did you ever get here? Okay. It could have been one of the last steps being a reduction, removing that functionality. Okay. Just something to watch out for. What? I'm not sure why this one's here in this order. That doesn't make any sense. I must have copied and pasted wrong. This is looking at our selectivity, our base choices for kinetic versus thermodynamic enolates. which we did talk about when we first looked at our enolates. That top one is our LDA. Okay, why is LDA going to give you that product?
The kinetic
How is that the kinetic product? Does anybody see any double bonds?
intermediate.
You may not see any double bonds, but remember, we have to remove our hydrogen first. Whoops. When we remove that hydrogen, we'd either be forming that as our enolate, or what is the difference between those enolates? Position of the pi bond, substitution of our pi bond. The purple one has more substitution, making it more stable. That's our thermodynamic enolate. Okay. So sometimes our kinetic versus thermodynamics are not obvious. Okay. We have to play around with those options and see what happens. Synthesis of propylbenzene, you all took that on the quiz. I forgot to check. How'd you guys do with that question? Anybody remember? I gave you 3 syntheses.
Yeah, I had a couple questions on that. There's one of them that I had never seen before. I'm like, why does this work?
So in the 3 syntheses, I believe, if I did it right, all 3 should have worked. We can pull that up. I don't remember what they are off the top of my head. If we got time, I'll pull that up so we can take a look at it. The next big section is our chromic acid, okay, our oxidation reactions. There are 2 reagents when it comes to oxidation that you really need to be super familiar with, particularly when oxidation involving oxygens. Chromic acid and PCC, which is really just chromic acid, okay, with some other stuff in it. Okay. When we run an oxidation reaction, all we're doing is increasing oxygen bonds. Both chromic acid and PCC will increase oxygen bonds. PCC, however, being politically correct, does not oxidize as far as just regular chromic acid. And I've gotten a couple people asking me why. Well, if we start with a primary alcohol and we take chromic acid, okay, well, number one, what do we see in chromic acid? What's reactive in that structure? Pi bonds. Okay, what can you tell me about pi bonds? Are they polar pi bonds? Do we have an electronegative element? And a not so electronegative element? So we have a polar pi bond, which means that chromium could act as an electrophile. I wonder if I have a nucleophile. Oh, wait, I do. And we end up doing a nucleophilic addition reaction, technically followed by an elimination, that ends up getting us to the structure, which is our chromate ester. The chromate ester can then do an internal elimination to get us to the aldehyde. How does that work? We take a base from solution, and we would end up with our aldehyde structure. Where's the base coming from if I'm using chromic acid? Could be coming from one of the oxygens in chromic acid, or it could be coming from water. What if it was PCC? There's no more water. It's likely coming from our pyridine. Okay, officially a deprotonated pyridine. Okay, so we can deprotonate that, and we'd be at the aldehyde. Both chromic acid and PCC get you there. So the question becomes is, well, why does chromic acid continue to react? Well, what did chromic acid react with? An alcohol. So clearly the aldehyde is an alcohol. That doesn't work. Why does chromic acid now all of a sudden make that aldehyde act like an alcohol? What does chromic acid also have present? What is special about water in the presence of aldehydes? They react to form, careful. They react to form the hydrate. What's special about the hydrate? What do I now have? What are those? Alcohols. What reacts with chromic acid? Alcohols. In the presence of water, the aldehyde becomes a hydrate, which is now an alcohol. That can react with chromic acid. Chromic acid can further oxidize. Why does PCC not do this? PCC does not have water. If there's no water, it can't react with the aldehyde. I don't have an alcohol. The reaction can't continue to oxidize. How do we know this to be true? What happens if we take PCC and we run that reaction and then add water to it? It oxidizes all the way down to the carboxylic acid. Okay? So it is that presence of water that's really driving these things. Up to you how much you want to remember of that. Ultimately, really all you need to know is what happens as an end result out of your oxidations. Chromic acid will oxidize as far as it can. So if it's a primary alcohol, we get a carboxylic acid. Secondary, a ketone. Primary, or tertiary, we would get no reaction. Why do we get no reaction in the tertiary? There's no hydrogen to remove from our carbon. We need that hydrogen. PCC will stop at the ketone, and aldehyde will also do no reaction with tertiaries. Protecting groups. Okay. This is a very thin one. We're going to skip through this pretty fast. Why skip through protecting groups? What is the point of a protecting group? To protect a functional group from other reactions. Okay. So we add a whole bunch of stuff to the structure so that it doesn't react, and then what do we need to do? Take all that stuff off. Okay. Put a bunch of armor on, take the armor off. Okay. As far as efficiency goes, is that something that's very efficient? No. If we want the armor, put the armor on, leave the armor on. We don't want the armor, don't ever put it on. Okay. That goes back to this idea of green chemistry. Protecting groups are generally not useful or not looked at favorably because you end up doing chemistry for the sake of doing chemistry, sort of. Okay? It does have a very important role, but the process of doing it now wastes chemicals. Okay? So if you are forced to do it, absolutely go for it. Okay? Otherwise, it is considered better to think smarter and avoid reactions or systems or structures that are going to require protecting groups. Okay. So we've seen some of these. You could use ethylene glycol. What kind of reaction is being run here? You could say protection. Let's avoid that. At first step, what did we make? Made an acetal. I wonder why we would talk about acetals. Oh, that's right, because we did already talk about them. Okay, that's why they're showing up as protecting groups. How do we get rid of the acetal? Water and acid, and we can reverse the reaction. Okay, the acetals will protect our carbonyls. Let's ignore the retrosynthesis for the moment. Protection of alcohols. There's a variety of ways to protect alcohols. Here they all are. How many of you want to memorize these? Okay, so yeah, me too. How about these? No. Yeah, me too. Okay. When it comes to protecting groups in the real world, what you would do is look them up. Okay. I'm not going to expect you to memorize them. I do expect you, however, if asked a question on the homework, to answer a question about them. Okay? Go look back at the retrosynthesis. That looks pretty ungodly. Sure, why not? Does that help anybody? Identifying pieces, seeing what you have, where they come from, how we could potentially put it together. So if I had to put this all together, this would probably be like the fourth step. No, I lied. It's the third step. What's that? Three is adding it to the electrophile. So one, starting with the para-bromobenzaldehyde, the very upper left, plus the diol, plus, or then followed by magnesium, then followed by the ketone, then followed by acid. The acid would protonate the alcohol, and it would also deprotect the acetal at the same step.